Hi everyone, welcome to Quant Seminar, I guess our 195th volume. Thanks for joining us today. My name is Lichi. I'm one of the organizers along with Terrence and Kristen here of this year's Quantitative Seminar series for the Quant Lab. I'll start off with a land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all bands and tribes in the Suquamish, Tulalip, and Muckleshoot Nation. Our lab also acknowledges that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. And now to introduce our speaker. Enrico is a PhD student from the University of Bologna in Italy and a current visit student in Andre Hunt's lab. He is involved in stock assessment evaluation for demersal fishery resources in the Mediterranean Sea and is interested in methodologies to incorporate ecological insights into fishery management systems. He's presenting part of his PhD results obtained while visiting, I don't know how to say this, Abo Academy University, Finland, and the Quant Lab. Enrico will take questions as we go after his introduction section. And so thanks everyone for coming today, and a big thank you to Enrico for sharing your work. And with that, turn it over to you.
Thank you everybody for coming. For me, it's a big pleasure and an honor to speak in front of you. So I will start by acknowledging the people that actually, okay, first problem. Yeah, we got it. The people that make this possible, starting from the first person that recommended me to look at this word of the your US fishery management and the risk table, which would be the figure behind my thought, which is Giuseppe Scarcella, my mentor, and then to Andre that helped me here with his support. Also permitted me to develop all this thing, and to Laura Usitalo and Enrica Puntilado that hosted me in Finland. And they are me developing the Bayesian network part, and Igor Celic and Simone Librelato that provided the ecological modeling component. So I will continue introducing why all of this and where all of this starts. So as Lichi said, I work in the Mediterranean Sea. I'm interested in stock assessment, and I've been participating to stock assessment meeting for a few years now. And a characteristic of this basin that is in Southern Europe, is just there, is that borders a huge amount of countries and 3 different continents. So it's an area with very diverse expertise, with diverse quality of data, and with some challenges going on, such as climate change, and also the political cooperation is not all the time simple, and this complicates the process of the stock assessment. And on top of that, we are really revising an astonishing number of assessments every year. This is the trend of the number of assessments that are revised within one single week every year. So we are talking about kind of 80 stock assessments. So all our stock assessment meeting ends up with just a reel of stock assessment, and there's no objective really way to evaluate them. So what I will try with my PhD to identify some more structured method to look into the problematic that can be associated with a particular stock assessment, to facilitate the validation, the uptake of the stock assessment, and also to point modelers toward solution on how to do better eventually. And the 3 kind of error that I'm trying to address within a stock assessment are the process error that is related to the stage where a fish is just a fish swimming in the ocean, so it's affected by environmental variability, the ecological processes, and these affect his life history parameters. Then when a fish dies, there's some probability that we record him, and some that we are missing. So that's where observation error arises, and then we try to model the data. We can barely specify our model, and we can break down these 3 components to identify the right solution and to optimize our effort toward improving our stock assessment. So again, this came from my supervisor that traveled because of MSc in different fisheries worldwide, and pointed me toward the approach you have here, you guys, that is quite an amazing approach, because In the North Pacific, you basically take a step back from the stock assessment and you look toward the big picture. You have instruments such as the ecosystem status report, where you collect a lot of information about the variability, the observed variability on your ecosystem. Then you have the ecosystem, the ESP ecosystem and social economic profile, where you try to link all these variability to a given stock. And then this process ends up in the risk table, which is a qualitative risk evaluation based on categories that tells you which is the perceived risk based on the modeler and on all this information on what I'm going through. How many of you are not familiar with the risk table? Okay. Okay. So
And you're out in the country like
yeah. So maybe I will spend a minute here. This is how a risk table look like in the way it is provided in the stock assessment and fishery evaluation report. So it's based on 4 categories. One is assessment related, where you try to summarize the concern related to model fits, model diagnostics. So mostly related to model error in this case. And then you have 3 categories that look at different, more on process related categories that are population dynamics, that the things you are looking at are there many years of recruitment failure, is the stock biomass suspiciously low for a number of years. So is there something concerning going on in the population dynamic coming from the stock assessment? Then environmental and ecosystem, you look at the environmental driver, their trend in recent years. So you try to think if in the next years there will be some increased concern related to the future state of this variable. You know, if your temperature is affecting the recruitment and the correlation is negative, if your temperature is increasing, probably you have an increased concern for this category. And then fishery performance, that is mostly related to some changes in the fishery system. For example, is there any evidence that the fishing strategy is changing, provoking a different bycatch dynamic? And each of these categories score in a qualitative sense from 1, that means like no risk, to 4, that is extreme concern. So basing on this, our aim was trying to again, I will try to reiterate this. I have in mind my background in the Mediterranean, so we really need to have objective ways and tools to allow people to repeat and to standardize their behavior, because otherwise it would be very hard considering our diversity. So I want to try to identify an objective method to provide information for these 3 kind of error I was talking about before, starting from the risk table, because I think it's a very comprehensive way to already summarize what's going on in your stock assessment and in the system you want to model. And 2 things that I wanted to consider was to consider the future state of nature, not just the past. So forecasting the system in the plausible future state of nature, and make use of available methods and data as much as possible. So I consider to break down this risk table in 2 different parts. One is assessment related consideration, because there are already a lot of methodology to kind of assign a scoring to the model quality and to the data coming from the assembled model weighing world, and put together these other 3 categories to try to reason in a driver pressure state response framework to make use of ecological model results for the future state of nature, and using a Bayesian network as a model envelope. Few words about the methods. So as I said, for what concern the stock assessment model evaluation, there's a lot of work that have been done in this CAPAM workshop or in different papers, mostly coming from the ensemble model weighting. And so when I jump into all these also material, I just say, okay, but on that part, I do not have to reinvent the wheel. I just would like to adapt what's in literature, my case study, and in particular, the kind of concept that I extracted from that work is that a weight of a model can be a composite indicator based on different categories that can be the convergence, the fit, the plausibility, the diagnostic, and expert. That expert can mean everything, basically. And using, when possible, this conversion table, because for some reason you have to assign qualitative scoring, for other you can use numbers. So that's the concept I will pick up later. While for describing the other three categories in terms of driver pressure, state, and response, I was inspired by this work from Laura Usitalo and colleagues, where they used different model results that are ecopath with ecosim and also biogeochemical model. And they used a Bayesian network as a model envelope to take the results, insert, putting in new questions, and to propagate their, well, I go through this later, but this was my framework that inspired me. So yeah, I try to explain better what a Bayesian network is, for who is not familiar. In this very simple, well, you can imagine like based on a graph and the conditional probability table that is behind the graph. And the graph is basically nodes and edges linking the nodes. And the state of each node depends. The probability that a given node is in a given state depends on the probability of its parents. So, for example, if we know that the train, there was a strike in the train, and that Martin was late, we would probably know that Martin was late too. And so again, we can use these properties to make inference and to propagate our belief on a particular, or our knowledge on a particular node, to propagate the effects in all across the system. Well, this goes probably very quick, but I hope you have the concept. Eventually, I can come back later. Okay, so this was the methodology very synthetically. What I'm going to do now, I will try to take you in a dive into my case study and to compile the risk table in its standard way. So collecting information, going through all these categories and assigning a qualitative score as it is supposed to be in the present method, because then I will compare this to the new methodology, and this will also serve for you to understand why I came to some conclusion. So my case study is common cuttlefish in the Adriatic Sea, that is this yellow area in the Mediterranean. And a few words on common cuttlefish. It's a cephalopod, and very important characteristics is that this guy lives a short life, but can grow very fast. So in less than 2 years can be more than 2 kilograms. The temperature trigger is metabolism, and he needs to eat a lot. And with increased temperature, we expect him to eat even more. And as soon as he's spawned, it dies because it's semi-porous. So these are the main features that we have to take in mind somehow. So first category I'm addressing on the risk table is environmental forcing. In these trends, what strikes is the temperature trend. This is the first panel there. So we see these trends are already detrended. So this is seasonalized. So there is no seasonality going on. It's just the mean. And we see that in 20 years, the temperature increased of 1 Celsius degree, and is likely to continue on this trend. The river input, there is no real signal. The primary production is increasing. The currents are, well, there was that spike in the early 2000s. And the dense water, that is another very important feature of the system, is not even giving us a precise signal. So trying to summarize input for the risk table, I will be concerned about the status of the bottom temperature and eventually of the primary production, while on the other trends, there's no clear signal. Going to the fishery aspect, I can talk a lot about the fishery in the Adriatic, but trying to keep it simple. It's all a sandy bottom basin, so trawlers are just everywhere, as you can see in these two pictures. But even if they are everywhere, over the recent time, the fleet capacity for the trawlers greatly decreased because of a combination of factors such as management plan, European effort to reduce the fishing capacity, but also depletion of stocks that so there was a point when fishers just doesn't find fishing so appealing and because they were catching not so much fish, and then also fuel price increase. So we observe this trajectory this is the first one in the trawlers. We also have a very important contribution of small scale fishery, that is a coastal fishery with different gears that can be pods, nets of different kinds. And in this case, it's hard to observe a real pattern. This depends on the gear. In pods, maybe we can see a decrease, but I will state that it's hard to have a real perception of the fishing days of small-scale fishery because there's probably underestimation or it's hard to control. So trying to summarize what's happening in the fishery, I would say that the bottom trawlers are not our main concern here, while the small-scale fishery can be, because I forgot to say this. There's one particular gear that targets spawners that are attracted to lay down their eggs, and when the fishermen clean their fishing device, they just kill the eggs. So it can be an additional source of mortality, not considering the stock assessment. Going to the ecological status, just briefly introducing the EcoPath with EcoSim model we have for the Adriatic Sea. It's a very complex model and quite comprehensive one, with a lot of functional group and trying to really have a perception of the complexity that has been trained over the 2005-2019 period. And the signal we are having from this ecological model, here I try to put on this side of the screen the prey of cuttlefish, which 2 out of 3 are decreasing in biomass, while on the other side we have the main competitors that are all increasing, and that kind of thing that concern me. And this trend is also confirming the stock assessment where available. These are the same species that are European hake, common sole, red mullet, and mantis shrimp, the main competitors, that in some way, all of them are recovering in status, probably also because of the reduction in fishing activity. While for the prey, we have some estimation from survey that confirm what's going on in the ecological model. So my takeaway from this to compile the risk table is that the status of the combined states of prey and predator can be somehow worrisome. And bonus information, there is also some invasive species that are spreading out in very recent year. That is this blue crab, and its impact is not yet clear, but can potentially be an additional source of concern. Population dynamic of cuttlefish. Top analysis, the biomass, you see a continuous decreasing trend, and for the last 10 years, the biomass has been around billion, and I think this is worrisome enough. And on top of that, this comes from the stock assessment model, which is a state-specific implementation of surplus production model, and the process error is not random, and in the last 10 years, it has been estimated to be below the average. So there's something probably going on in population dynamic, and this is my takeaway for the risk table. And coming to the stock assessment, again, there's a typo here, is the Java model. So trying to see the quality of the stock assessment is well, the model converge, there's no major failure in the residual. The quality of data is acceptable. We can have some issue in the quality of the reporting from the small-scale fishery. Probably there is some underestimation. The survey is representative. There is a good catchability, but in the last 3 years, we had some problem. We missed the part of the reduce the coverage, so we implemented a model-based estimation. And coming to more diagnostic, we see some, the fit to the survey data is acceptable. Again, there are some points that are not properly taken, but on averages, well, at least compared to the average quality of the fit in the Mediterranean is not very bad. The diagnostics are within the boundary of the Monroe, but we have some not, well, I would say some very bad predictive power. So trying to summarize this, the main issue are low predictive power of the model and some issue in data quality. This leads to compiling the risk table in the standard way, I think, and the main points lead to this scoring. So the major problem is in the environment and ecosystem, that is from my perspective of level 3, so substantially increased concern. I will assign a score of 2 to stock assessment population dynamic and no concern for the fishery performance. So now in the next 20 minutes, I will try to summarize what I've done, trying to put new. So this is the implementation of that model scoring for the stock assessment. Is a hierarchical, is that just a hierarchical scoring based on different levels, where the basic level is just a combination of the main diagnostics. So this is adapted to my surplus production model, of course, can be modified based on your necessities. It's just an example. So we are assessing convergence, prior update, goodness of fit, consistency, prediction skill, and on a pass or fail basis, where the pass or fail is based on an objective metric when available, or otherwise on expert judgment. We combine all of this information into a single metric that is 1 if at least 70% of the metrics are passed, or otherwise is 0. And on the level 2, we combine all of them, taking just the average. And on this level 2, we are putting back in the data quality. So we assign a score based on the expert evaluation on the quality of the catch and the index, which in my case was 75, 0.75, because there are some problems, but not so major problems. And this leads us to the first level, where we are having another combined indicator that is an average. You can assign a different weight, of course, if you think is the case, combining model error, so in our case is 0.8, and observation error, that is 0.75. If we want, we can assign a unique number to the assessment score just by averaging or using a different weight. This is, again, really depending on the frame. Well, the idea behind this is to provide a concept, then you can adapt it to your necessity very, very easily. And so we end up with an assessment score of 0.775. From this moment, if you have questions, I'm happy to taking them. And this is the most of the work I have started doing last year, and I really improved during my month here. So the idea is to describe these other 3 categories in terms of driver, pressure, state, and response, including the ecological model. What does this mean? So means, first thing, building a conceptual map of the concept that we are seeing in the risk table. On the first level, we put the drivers that are high-level activities that we can have control on it sometime, because, well, we can't really control climate. We can control fishing or other anthropogenic pressure. Then we put the pressure that are variable, that have an impact on our target stock and that we can estimate. Then another level is the state of some property of our stock that we can measure and is affected. And on the lower level, there's the response, that is a property that can trigger our management intervention. But so far, there's not enough space to formulate the connection between the pressure and the state. So that's why we are adding an additional layer that is the process, that is the biological pathway through how the pressure will affect the state. In another way around is what is the functional response of the state to the pressure. And to our case study, I identified three main processes that can be going on in this conceptual map. The first one is the effect of the food web and of the temperature on the growth, summarizing, of our stock. Another one is the effect of that bycatch effect in the fishery that can be an additional source of mortality that so far is not really taken into account in stock assessment. And I put a question mark on invasive species because maybe, but we don't know. So to be pragmatic, we have to discard those processes that we don't really have information on, because on this spot bycatch, there's no real data and no real information. But otherwise, on the food web and temperature component, there's some information that we can use to see how this biological process can respond to a future state of nature. And to do this, so we try to break down this process of the growth in breaking it down in tiny parts. So we can see growth as a function of energetic budget, that is just food intake minus the metabolic consumption minus the excretion of the loss. And each of these parts can be broke down even more into its minimal element, that for the food are the availability of prey, the suitability of the prey, the competition, and the temperature, because remember, in our specific case, temperature trigger the appetite way, and the metabolic expense is also a function of temperature. How to put this machinery working? Well, we can try to define equation linking all of these nodes and find the source of data to modulate the upper level, which is in this case the ecopath results to have an estimation of the state of the food web, so the prey and the competitor in future scenarios, the RCP scenarios for the state of temperature in the future, and a lot of work that has been already done to put all this together. For example, the predator prey suitability from the Seattle model. It's a way to see how an amount of prey can respond, can be suitable for our predator. Or there's interference competition that is based on this other equation that is sort of a crowding effect. So when there's a lot of predator, it's not just the consumption of the predator that can affect the availability of prey, but it's also the elements in the system. Okay. So we see that for each of these components, there's some sort of equation that can help us to see how to modulate to propagate the effect. But there's a question mark. We don't know how to trigger the appetite on the temperature. And that's the work I've been doing here. Fortunately for cuttlefish, there's a lot of data from aquaculture experiments where they test a different protocol at different temperature and food intake, and then take repeated measurements of the growth. So we collected this data from 19 different publications, leading to 69 different treatments, so combination of temperature and food, and we applied a meta-analysis to summarize all of the information and to infer the response to these two drivers for an unobserved population. And we implemented this meta-analysis as a hierarchical Bayesian model using STAN. And to do this, we had to do another assumption, because most of the time the food was provided at Lipitune, that means all you can eat, basically. So these overcompensate for the metabolic loss. So when, and we introduced this new notation that is peak common. And I'm sure that this is, my presentation is a great example for scientific notation that sometimes can be really, we were talking about this, sorry, in the class this morning. It's very complicated sometimes. So when P comma is 1 means that the growth is just a function of temperature, otherwise it's both a function of temperature and P comma. This is the shape of the response of the growth rate to during the time. So we have a first phase when the growth is very high, and then there is a decline and going to stabilize after 2 months of life. And the time frame we are modeling is restricted to here, so from 0 to 6 months. So we define two different equations for the response to the growth rate to time, which is a Gaussian for the first 60 days to modulate this peak and the decline, and an exponential decay for the second part of the growth. And we try to introduce the effect of the covariate as for the first part of the life stage, the fixed effect of the temperature and of the prey are the height of the peak and the curvature of the peak in an additive way, while the random effect is on the location of the peak. This is to allow difference between experimental setting that maybe there is some error in inferring the exact age. While in the adult life stage, I will show you this why later, but basically we didn't have so many data in the period between 80 and 100 days. That's why we use the fixed effect to scale the asymptotic length, while for the rate of decline, we are considering a unique parameter, and the random effect is on the start of the, so on the age of this function that is kind to match the random effect in the juvenile model. I hope this was clear enough. The assumption we are doing is that the breakpoint is exactly at 60 days and there is an asymptotic growth rate. This is not exactly true. So we tested different model configuration before to come up with this, but and we did our model selection with RMC, LPD, LU, and posterior. Anyway, so this is the fit to the data for the juvenile model. So these are all the different treatment we test. The message here is that we had a lot of information and contrast in the juvenile stage. The color represents the different level of food, and the temperature is kind of not exactly easy to grasp. So lower temperature, higher temperature is just good row by row. And the residual tell us that we are kind of doing well in getting the information. While for these are the same thing for the adult model. So the first thing we see that we have really less information for the adult. There's not so much contrast in the food, and we really have no information basically for the first part. That's why we couldn't estimate any more. We let it random, but again, the residual are kind of okay. So we think that the parameter we are trying to estimate, well, we are doing a nice job on it. The prior were updated, and so we can try to estimate the functional response, the effect of the covariate on the model. So in both cases, on the left side, there's the intake. Okay, I forgot to say this, that this formulation allows the concavity of the response to be determined by the data, and we are not imposing the shape. So the response of the food is an exponential, while the response to temperature is slowing down. So we can sample the posterior to predict the growth rate at different temperature. We put this together. It's doing a nice job in predicting the our data. And what we can do now, we can use the growth to predict the weight. So we can anchor our model estimate to reality and use this to anchor. Let me reformulate this, sorry. If we assume that a given state of nature produce a given weight, we can use our model posteriors to find which is the best combination of temperature and intake that predict that kind of weight distribution. And if we know that in that moment, the state of nature predicted a weight distribution, we have ecological model. So we can say that in that period, that's the state of nature. And this is the process that allow us to connect this modeling to the ecological part. So basically, we are dividing our P to the observed distribution of biomass in the same time frame from where this observation come from. And so we can use all of this information to come over this gap. We do a simplification. So we say that the effect of temperature is triggering the search rate of our species, basically. So more temperature means more food. And with all this machinery all together, we are ready to simulate data to train our Bayesian network and to see what happened when we put together everything. So this is the final structure of the Bayesian network. We divide each of the tiny components into life stage. So we have the state of the prey and the competitor again that is informed by ecopath. We have the interference competition that can affect their interaction. We have different time frame and we have the effect of temperature. We are simulating all the data based on the equation. We are discretizing them using training data to feed the Bayesian network that is learning, and we can use that model envelope to condition decision nodes that are food web status, temperature, and interference competition as an assumption, is that true or no, to see how the utility node, that in our case is the weight, would response. We can then measure the risk. And let me try to state the context on how our objectives and what the risk means. So our intervention is to compare the probability that the weight can be in a different status, the potential weight, and accounting for, of course, all the other population dynamic component. It's just the potential weight can be. We are comparing future to present, and the present is very bad. So our objective is to recover, to really improve from the present. So the meaning of risk in our case is that if we are in the same state or we get worse, we are already in a risky state. So we really want the future to be way better than the present. And the scenario we are testing are 4 combination of things. 3 scenario, 3 food web from.
Go back to the XFC.
Yeah, thank you for coming. So, future scenario from food web status from ecopath, a baseline, effort reduction, and primary productivity increase. I will show you later what does this mean. Temperature that is equal to what observed in our reference period or 1 Celsius degree more, according to RCP. Interference competition, yes or no. And 2 different time frames. So 2020 to 2025 or 2020 to 2030. And just to give you a anticipation on how what the results can look like. So these are the 3 different ecopath scenario. The baseline is the blue one. In any case, the preys are declining more and more, and the competitors are or increasing or oscillating, basically. And so okay, I forgot to say a thing. To estimate our risk, we are iterating, we are repeatedly sampling from the Bayesian network conditioning from a random sample from the distribution of the status of the food web in the time frame observed. So our baseline is this distribution of this period and the 2 different time frame future or this other one random. So coming to our result, another thing, there's no historical condition on this. So there is no past that we cannot know how the distribution was when cuttlefish was doing great. So this is the reference distribution of the weight categories that are low, medium, high, very high, or even very low. And these are the predicted distribution based on the combination of scenario in the 2025 horizon or 2030. So first thing we see that the near future is very similar to the present, while in 2030 we see a decreased probability to be in a very high status. And when we try to translate this into risk probability, we see that, okay, this table, how to read this table? Here we have short-term horizon, long-term horizon. The panels are representing the ecological model results. The red dots are for the no interference competition. Blue dots are interference competition, yes, and the triangles are for 1 degree more. So, well, the future is 2030 is worse than 2025. Interference competition will, as expected, increase the risk, and temperature will decrease the risk. There's no way that we end up in a very good status, only one scenario, but there are not even ways that we end up in a very bad scenario. So most likely we are all remaining kind of the same, or we are doing slightly worse. But I will try to provide this result in a different fashion. So, because what if we ignore the state of the temperature? We want to test in uncertainty on this. We can aggregate our result, and as expected, the risk is shrinking toward the mean, and we can repeat this again, ignoring also the competition. And on this final, that is conserving the main properties, is just shrinking toward the mean of the result, of course. And this picture will say again that in the next future, we have some probability to do slightly better, while in 2030, there's no way we end up in a recovering status for our cuttlefish. So trying to put all this together and comparing to the risk table, what's new? What's the advantage of putting so much effort? Well, first thing is that we can break down our scoring into the reason why a score is given. So we can anchor our probability to a given set of conditions that then the stakeholder can evaluate what they believe more or what they can control more. Yeah, and it's probably easier to communicate passing through the conceptual model why you think that your process is going to be at risk. So improving communicability, and I would say maybe not credibility, probably is not the right word, but well, acceptance of why a number is coming like that. And again, this will also allow the possibility to explore alternative risk objectives, because, well, when you have that Bayesian model and you have all your machinery working, you can really try to play with your, what do you mean with risk, what you want to get out, how to combine scenario. And probably I gave a very complicated example on how this can be done, but imagine that somebody has already made up the meta-analysis for you, so you can just use models. So the message here is to try to use the best available knowledge, and if you really need to do an additional model, but if you already have all the elements to link the pressure to the state throughout processes based on available knowledge, well, you are in the best case possible. And what we learn for catfish, so coming back to the title, better model data or process knowledge. Well, I would say that with the actual model, there's not so much we can do to improve unless we are changing completely the model. For the data, there are some problems, but again, it would be very hard to improve on these aspects because the past is the past. We cannot change the data collection in the 80s or in the early 2000s, and small scale there we are not really ready to find a solution to improve the data collection on the small scale fishery. But we have really improved the understanding of what can happen on this process. So I think that I will really focus on the process and hopefully one day maybe try to build up a population dynamic model that can take this information and see how a modification of a life story, if story parameter can propagate throughout the life and the biomass estimation. So to end up maybe with a reference point, improve the reference point. When concluding, well, why this is useful in the GFCN context, on top of why is this useful in general. The assessment scoring is a very powerful instrument in our framework. Even if I dedicated probably 1 minute here, we really need that part already. I already presented, I presented a few of these results, and everybody was so happy to see a objective way to compare models that will allow to compare the results across maybe the same species model with the same method across different areas of the Mediterranean. So to have a more objective way to accept or reject the models, and also point others to how to improve in the future, and what the Bayesian network in general can do, can force people to put together a conceptual map, can force people to try to find the data and the solution to deal with how to propagate their expert belief through a objective measure or function, and see how the system will react. And also, last but not least, it's also a way to make a better uptake of ecological model results that so far, I think, to my understanding, our ecological model is a word where there is a lot of work put in, but so far we are not really taking the best out of it, at least in the Mediterranean, where now we have basically an ecopath with ecosim model for each corner of the Mediterranean, but nobody used that information, at least in the stock assessment world. Yeah, and yeah, I already went through half this, and I think I'm done here. So thank you for listening.
Thank you, Enrico. That was a lot of work.
A lot of words. Sorry.
Yeah, so we have some time for questions. Folks in the room, we'll start with folks in the room, and if not, we do have questions online as well. So.
I'm sorry to show that I didn't really follow it, but can you repeat what I don't think all of the functions in the Bayesian network were known a priori, and some of them you learned from meta-analysis.
Yeah.
So how is that fitted, and what was the data that it was fitted to?
Thank you. Yeah. Sure. So our first version of the machinery was well, the only information we were missing was the effect of the temperature on the food intake. So we know that more temperature probably will cause more intake, and this will affect the growth, because an experiment basically say that if you grow cuttlefish in a higher temperature, you will increase the growth. So our meta-analysis was trying to inferring the expected functional response of the growth to the temperature and the food. So these, yeah.
So all the other arrows represent functions that you
All
do
the
a priori.
all the other, yeah, were known a priori from mostly from literature, or we made up in a very well, the most obvious one we just made up, like multiplying the biomass by joules. That is, I think, was fair enough to approximate. While the other, yeah, for example, yeah, this S is just the predator prey suitability from Seattle that is informed from diet content. Yeah, I haven't said that, sorry. Yeah, so we put extra information. We put the trophic matrix, again, from literature, and we use that with the biomass of the food web throughout the system to infer how much of each prey will contribute to the diet, so to the combined intake. So yeah, everything was known a priori because of the work. That was also the message I wanted to spread. So if you already have somebody that made the job for you, that's also just using it. But yeah, we missed one tiny part of the thing. That's our job here.
I think.
I'm not sure I understand, but when you're showing the results of the diagonal network simulation, you're then aggregating some scenarios results. Like to,
Yeah, you can do it.
so is that what you were doing or not? Because you're showing like a lot of points and then fewer points.
Yeah, exactly. Because when you to make inference in a Bayesian network, you have these decision nodes that are the nodes where you can control the state, but you can also ignore the state of those nodes. So in the first plot I show, I was saying that I knew the status of each of the food web, the time frame, the temperature, and the competition. But what if I want to test the uncertainty about one of these decision nodes? So in the other plot, I was just not putting any constraint. I wasn't conditioning the probability of the temperature, for example. I was conditioning all the other one. And in the later plot, I was also let the another decision not to be free. That was the.
Okay, I think I understand, but why is it not resulting in having some confidence interval?
Yeah, sure. Because that's just because the way we are calculating where it is. The risk, we are taking the distribution that, if you remember, well, jumping in and out from slides. So here we have confidence interval because these are actually the results of the Bayesian network. So we have a probability distribution of our way to be in a given state. But because how we are calculating the risk now, we are just sampling that distribution, and at the same time we are sampling the baseline distribution, and we are just counting the number of time we result in a different status. We can add confidence interval here, iterating this procedure multiple times, of course. Well, yeah, okay. Is that clear? No, okay. We are just sampling one number at a time for a 1,000 times from both distribution, and we on each single iteration is this lower or higher because it's qualitative, and then we are just counting. This is how the risk is given now. Totally agree that can be improved. This was the last part of the thing that went together really in the last few days, so it's to be improved. Thank you for pointing out that. I think I'll be no, I don't. But
Yeah, I was wondering, I really like the idea of putting all this information into risk table. In your system, would you think that cuttlefish is a data-rich species? And how feasible do you think this is for the other 80 stock assessments that they said that you guys have to review each year? But how portable do you think this could be?
Thank you for the question. It's I will see hopefully how this works. But well, there's a part of the thing for which we have data. So all the environmental information, there are open source data that can help us to see how the system is. And on the single species, maybe we can have less data for a given species, but I'm sure that there are a lot of people with expertise on single species. So we can see how this will evolve when we have less data, but some expert belief maybe, or borrowing parameter from other stock. But sure, the advantage will be to try to break down the perception of people regarding a stock that so far has have been really disregarded. So, but yeah, I see your point. Probably this is a rich, especially for the aquaculture experiment. But yeah, hopefully we will try to replicate this image, and I will let you know.
We have a lot of questions online.
Oh,
We had 3 people ask the same one, basically, from Jim Mianelli, Giuseppe, and Abby Golden, asking about how you would integrate this approach into management advice, or what kind of management advice would come from
My question.
great.
Risk table you explained was pretty easy to communicate. And this is a much more complicated risk assessment process. And how would you change the way you communicate risk coming from this process rather than the more subjective stoplight process?
Okay, thank you for sure this is a very important point. So at first I saw this way to communicate the risk and improvement compared to the standard one, because allow the modeler, so who already managed the complexity, to base its consideration on a more robust feeling, not just on quality. So if you have to state on your stock assessment report the rationale why, you have to provide a buffer between the OFL and the ABC different. You know, that's why there are the rules, and so I'm more from this perspective. I acknowledge it. For the public can be harder, but a good property of the Bayesian network is that you can, well, imagine if this would be a shiny app, you can sit with managers, allow them to play with some leverage to see how their different hypotheses on the future state will affect the result. So it's still complex maybe, but it's more suitable to be used in a participatory approach where you provide the basis, and the higher level people or the less scientific people can play with their idea and see the result through how your perception and throughout data, of course. Then how to put this in a management framework such as the Mediterranean Sea? Oh, that's a unsolved question, because so far there's not even the way to do this. There's no risk framework at all in the Mediterranean Sea. So no solution now, but this would be maybe a first time to start talking about this and to try to put the risk concept within a framework where we still don't have this concept, and see the uptake of people, start to talk about it, and then gathering idea from other people, from scientists as well as from the higher level GFCM representative, and to reason together on how to put this into reality, basically. Not sure I haven't answered, but yeah. hard to answer. It's very important.
There are a couple more comments online, but I want to just acknowledge it is 1:30, so it's the end of our time here. We both need to leave. If you want to hear those questions, we can go through them.
Yeah, sure.
But before we get there, I think Enrico.
Thank you.
Yeah, he said they had some very long questions.
Oh, can I read it through
Yeah,
the
you can
chat?
read it. It's in the chat bar.
Yeah.
There's two questions.
Where is the? Oh my. Okay.
Oh, she was. Those kind of seem like, yeah,
It could be.
I know.
But it's still, I don't know.
Okay. Well, Giuseppe, are just me and you, I think now. I don't know if there is still people
Yeah,
online, but okay. Well, for the recruitment, I think that we really need a population dynamic model for that because actually recruitment can really be a function of growth because growth is a property of our species that can be reflected in other kind of properties such as natural mortality first that can then impact the recruitment because the growth impact the size at age. So we know that for cephalopods, the size at age, especially in the first part of the life, is critical for the survival. So we can translate a difference in growth in mortality, for example, and to see how this propagates. But to do any kind of inference on some, let's say, stock assessment quantity, we really need to pass, in my opinion, through our population dynamic model because otherwise we will have to build a different conceptual model, but it's very hard, I think, to talk about recruitment just on beliefs because it's a very hard to measure quantity and there is not enough information in literature to say what is driving the recruitment. We can just estimating it through a population dynamic model. I think. Then other question.
So I think it's talking about the effort, like other ways of considering effort or measuring effort and how we can incorporate those factors such as number of years into the risk assessment table.
Okay. I think also for that we will need a different conceptual, not a different conceptual model, but we have to deal with a different process. And so we need some information, I think, if we want to model the effect of, well, the number of years. I see this as a more stock assessment related question. So we can model the fishing exploitation and it's again, I think it's more suitable for a population dynamic model, I think. On the question number 3, yeah,
I think you mostly answered that one.
Okay, integrate the output of the risk assessment into the advice. Yeah, I think so. That basically, I haven't talked a lot about this, but the EcoPath projection show us that reducing the effort is not really doing anything good for cuttlefish because probably other competitors are increasing and prey are declining. So totally the strategy can be to focus on the small scale fishery. And well, actually thank you for this because yeah, I haven't really thought in that term, but actually it's a way to see the results. So putting more effort toward controlling the small scale fishery because of tourism, because of the uncertainty around that mortality, and because so far it's basically uncontrolled. So yeah, thank you. That's I have to keep track of.
Yeah, it'll be saved. All these questions are saved.
Okay.
Thank you, Enrico. Thank you.
Hi, and says that it's great to see that you have this work that builds on the original risk table.
I'm very happy that Martin was here to hear all this, because yeah, the risk table was a great inspiration for all this work. And well, again, acknowledging Giuseppe that introduced me to this concept first time, but really it's a great way to take a step back from all the complexity that there is a stock assessment and see the system from the outside, and so to think on where is the major problem. So yeah, it's a great framework, and well, I hope I provide some food for thought for the future. Thank you.
I think that those were most of the questions that were online. Hopefully, if anyone else has anything to ask, feel free to raise your hand. I can allow you to talk, or we can post it in the chat box. A couple seconds. Thanks. Thanks for joining us. Yeah, see you next week.
Thank you, everyone.